Hello, everyone. Welcome to the first day of CCIE Enterprise 1.1. Today's session is divided into two different sections. First of all is going to be the introductory section where we'll talk about the syllabus, how the lab is. I'm not going to waste much time here, but just it will be a small overview of the whole engagement. Then we'll quickly start with the syllabus. And we're going to be starting with the switched campus for today's session. Today's agenda is going to be, obviously, I'll talk a little bit about trainer's introduction. We'll see the syllabus overview and lab exam walkthrough as well. The whole course is going to be taught by me. Well, I'm Saif Deshmukh, and Murtuza Ali as well. We both have almost 10 years of experience, especially Murtuza have more than 90 years of experience in the networking field. And his specializations are in service provider side of technologies like MPLS, BGP, and architect level OSPF design as well. Me, I have more than 10 years of experience. I'm specialized into SD-WAN related technologies like SD-WAN, SD-Access. I've worked with many S&P 500 Fortune companies. Let's talk about the syllabus overview. Well, the CCIE lab is what we're talking about. It's divided into 5 distinct modules, namely the network infrastructure. Here you have what we used to know of routing and switching before 2019 have been summarized into roughly 15% of inside of network infrastructure. Your SDN related technologies. Excuse me, anybody have any questions? Try to be on mute, guys. If you need anything, you can raise your hand. I'll stop and ask you. So the second module is software-defined networking. Here you have SD-WAN and SD-Access. We will talk about it in detail about the syllabus. Third is transport technology. This is covering your MPLS and DM VPN. Infrastructure security and services. You have IP services, IPv6 security related features and quality of service as well. Basically, optimization related and IP services related topics are added in this specific module. Number 5 is regarding the automation and programmability. Some part of network infrastructure is going to be taught by me. Since most of the specialization is into BGP, he is going to cover the BGP and routing aspects, especially MPLS side. The whole software-defined networking and transport technologies are going to be covered by me, like DMVPN, but MPLS is going to be covered by the Murtuza. And infrastructure security and services, it's a mix of both. And complete automation and programmability is going to be taught by Murtuza. So if you talk about the module 1, this is what you'll see as a sub-modules. The network infrastructure is divided into 6 sub-modules in it. This is the switching campus. So here's the thing. One of the main reasons why I'm talking about the syllabus is it should tell you how much value you should give to that topic. We should understand this is the 15% of the actual syllabus. So we might want to consider how much time are we giving it. Switch campus covers your spanning tree. 3 main topics are there. 3 main topics are switch spanning tree, you have Ether channel, and VLAN. Many of the older technologies they have removed. You don't have VTP, you don't have GLBP. They have also removed the PAGP as well from Ether channel. So basically you have LACP and static only. VLAN, pretty basic stuff. Okay, the native VLAN. So you should know just about the type of VLANs. You should know about the tagging methods, spatially focuses on 80.1Q. This is precisely taken from the blueprint. Nothing's changed. So what you're seeing is exactly going to come. If it's not mentioned here, it's not going to be in the lab. So don't even waste reading one line, even 1 second on that extra part. Maybe after getting the number, maybe you can do that. Unless your specific goal is to learn the topic rather than passing the exam, then that's a different story. Some smaller topic would be switch administration, layer 2 protocols like CDP, LLDP, UDLD. These things are added here. So we're not going to be considering these as a separate topic or separate classes. Rather, these things are taught into as part of the other things. So for instance, if I give an example, we're not going to talk about especially what is air disable recovery in detail. Rather, we'll talk about air disable recovery. And air disable might have happened because of some reason in ether channel or some reason in spanning tree, like that. But main topic in switch campus, to focus on specific parts, we will cover these main 3 distinct parts. Today's session, we're going to be discussing about the spanning tree directly. So after this, everything is routing. What they did, in 1.2, they have laid the foundation of in 1.2, they have laid the foundation of routing concepts, like what is AD. This might seem like a basic stuff, but we'll still go through it. What you should pay attention here is that things like, for instance, the route leaking, you have route filtering, a redistribution between different routing protocols, and authentication. It's not taught as a separate topic. Rather, when we'll talk about OSPF, we will cover the authentication of OSPF, right? Redistribution of OSPF. So from 1.2F, or excuse me, 1.2G route filtering, all the way till 1.2J bidirectional forward integration is taught separately into each topic and their use cases in those routing protocols. In EIGRP, the focus is definitely on the named mode here, but we will cover both classical and named EIGRP. We will talk about details of base path selection, what is the difference between both versions. In the exam, definitely at least one question you can expect regarding EIGRP named mode configuration. About the OSPF, you have version 2 and version 3. The main focus regarding is going to be regarding the version 2 here. We will cover all the advanced topic that is taught and in very detail, whether it's the EIGRP or OSPF. We will go as detailed as possible, especially in each section. Once we cover EIGRP, we will definitely, it's not going to be revealed, but we will cover things that have been in the exams since past 5 years regarding that topic. We will be unknowingly cover the topics or questions that came related to the OSPF, for instance, since past years. We'll do the same thing with the BGP and multicast as well. If you talk about the BGP specifically, which is going to be taught by Murtuza, it's going to be kind of like a long class. It may take roughly 2 weeks, which is again 4 class. So all the topics like IBGP, eBGP relations, all the subtopic related to it, path selection, routing policies will be heavily considered here. Definitely workbook also going to be having a lot of scenarios that will cover routing policy section, because regardless of the year or version, at least 2 to 3 questions came about the BGP in the lab exam. So we will cover those when the time arrives. Path manipulation and convergence and scalability topics are also here, which we're going to cover. Multicast, again, which is going to be taken by the Murtaza. We're going to take the layer 2 multicast. You have reverse path forwarding check as well. PIM related topics are also there. If we talk about the module 2, the module 2 have 2 subsections, SD access and SD WAN. Now, here's a usual question that I get. This is not covering the whole product, the product as a whole. right? Rather, it's focusing on the lab exam. So because of that, they're still stuck in the older version. They're not going to have what is the latest SD-WAN. They're not going to have latest SD access also. If we talk about SD access, we'll talk about all the underlay technologies, like how to onboard the switches manually, obviously using Catalyst Center, or otherwise known as a DNAC. We'll see how to perform LAN automation and PNP device discovery, and we'll talk about what are the extended nodes and policy extended nodes as well. We'll talk about overlay. We'll dive deep into Lisp operation. Okay, some of the people are here that have taken this access class. They know that I go in very detail regarding the Lisp. We'll see what is the alternate option for the control plane we have apart from Lisp, which is BGP control plane. We'll see at the data plane how VXLAN functions. So when we talk about VXLAN, it's not as detailed as we get to look at it inside of data center. The use case is, I would say, less than 90% than what you get in data center. We'll see. Obviously, since ICE is also going to be part of SD access, you will have a trust check policies as well, right? We're gonna talk about the security group tags, the micro segmentation and macro segmentation as well. Multicast related topics are also going to be covered here. We'll see how to design the fabric, uh, because the SD access behaves differently in different type of design. When you have a single box, it behaves differently. When you have multi-site, it behaves differently. So we'll cover these topic, the fabric design, regarding the fabric deployment. Now this is where all the dots are going to be connected. A little bit of wireless is also going to be taken, even though it's not covered in the syllabus. Wireless as in how to onboard the access points, how do you create SSIDs, how everything connects as a whole to make the SD access. And we'll talk about the host onboarding, authentication templates, port configuration. If it's okay if you're not able to get like majority of the things that I'm saying, but eventually we'll get to those topics in detail as well. And it's going to be heavily practical, especially these two major topics, the access and SD-WAN. Part of the reason is because you have separate section in the lab exam. Right? You have 6 to 7 questions just regarding the SD-WAN and SD access. It depends on which version we are talking about. Okay, we'll see in the traffic that is inside of the SD access, how does it get outside of it? Like we have something called borders, right? So inside of SD access, what kind of border we have, what options do we have? All these topics we're going to talk about. Segmentation, I already talked about it. Macro segmentation, micro level segmentation is going to be covered. Again, SD access as a whole is really a big topic. This is, I would say, a fair chunk of the actual product. But still, it's not covering the full product itself. If you talk about this D-WAN, here we're going to talk about the control architectures. We have like all the controllers, management plane, orchestrational control plane, all these different controllers are there. How do they interact with each other and with the data plane as well? We'll talk about the underlay, the different type of deployment options you have. So even though this option doesn't belong in the lab exam because they're not going to tell you to onboard some devices, okay? Still, we will see the deployment options available, like how do you deploy the managed router on any cloud, right? Since you have a VM option available, the WAN edge router, the router that is sitting at the core of the network or the edge of the network, how do you deploy it in multiple type of platforms like AWS, Azure, even VMware, let's say. Okay, so we'll see how does it behave in terms of deployment of greenfield, brownfields, and a mix-up or a hybrid kind of deployment. Okay. After the deployment, we'll see like these system configurations related stuff like system IP, site ID, organization name. These are the things we already have taken in the controller architecture already. But we will, it doesn't have to, what I'm saying is we don't have to follow what you're seeing here. So we don't have to take first control architecture. We may talk about something else. Eventually, by the time we finish SD-WAN, we will have covered all these topics plus some extra topics as well. So if you feel like I'm not following what you're seeing in the blueprint, but eventually you should be checking the as a checklist if you have taken that specific point or not. Okay, the big boy, OMP, Overlay Management Protocol. We will talk about the attributes of it, because this is a protocol. I would say in a plain language, this acts like a routing protocol. We will see how it behaves with SD-WAN, right? We'll talk about its attributes. How does the data plane works? The key, IP key management, the route aggregation, the distribution options you have available, route linking between different VPNs. All these things we're going to talk about it with the OMP. Regarding the management, like you have like 100 sets of devices you want to manage using templates. So we will see, even though this is something that is, I would say, considered as some classical technology, because you have something called configuration groups. This is launched kind of like last year. So it's, what I'm saying is, even though you have some old and topics that are going to be obsolete, they're still part of the lab exam. Okay. So configuration group, we're going to take CLI templates, feature, device templates, all these topics we will take in as practical as well. And even though SD-WAN and SD access are kind of like resource intensive labs, you still will have a separate lab assigned regardless of how much time you're utilizing in there, as long as you want. We'll talk about policies, because literally policy is, I will say, without policy there is no SD-WAN, and it's just like a automated DMV and otherwise. That's all it is. So using policies, we'll see what are the centralized policies, localized policies, how we can create hub and spoke topologies. Here, they didn't talk about hub and spoke, but they talked about some names here that using those, we can achieve that result, like hub and spoke, full mesh, all those things. In the exam, you will have at least 2 questions regarding the policies. Module 3 is transport technologies. The 3.1 is very basic topic, a static P2P and GRD tunnels, really basic GRD tunnels we're going to talk about here. 3.2 is MPLS. So a little bit different, what we are going to do is, after we have taken the BGP, after that we'll take MPLS directly. Okay, and then GRD. So in MPLS, even in MPLS, specifically layer 3 VPN they are talking about. So we will see how LDP works, how the operations work. No L2 VPN, because it's not relevant to the lab, CCIE lab. So you can expect at least 1 question regarding MPLS in the lab exam. So you should be able to know how L3 VPNs are formed. Obviously, without LDP and without these operations, you will not be able to understand that, obviously. In L3 VPN, you should be able to troubleshoot the L3 VPN as well. You should know what is the provider edge, customer edge, how does the route leaking happens in there as well, all these things. Okay, the VPN, here you have a specific scenario. You should be able to understand how to troubleshoot phase 3 dual hub design. They're not talking about phase 1, they're not talking about phase 2. Even though that's something weak area, you should be able to at least know about phase 3 design. Okay. So module 4 might seem like a really big section or module, but these are like all these 7 modules are really small. So it's a mix of all the small sections and create it as a module 4 as a whole. 4.2 is really, 4.1 is small. We're talking about AAA, you should be able to understand control plane policing. 4.2 is network security. Talking about like 4.2 is talking about switch security features, router security features. I told you about the IPv6 infrastructure security features as well. 4.3 is the system management. Here, all the stuff that we use to manage the systems, whether it's logging, device management, SNMP is taken here. The lab exam is so huge, do you have so much to cover? You don't, even if something that is going to come from the module 4 is going to be in a really small portion. It's not going to be a separate question, rather it's going to be a part of question. Along with other things, they might tell you to just do something or achieve something in that. Obviously, quality of service. We have the SCP classification, right? Policy shaping. We're gonna see condition management, end-to-end layer 3 QoS, modular MQC is also there, modular QoS. Now, network services, what I've seen is this heavily comes in the exam, at least one question. So FHRP flavors are there, right, for V4 and virtual V6 as well, NTP, DHCP related stuff, and network address translation related objectives are also there. For network optimization, IPSLA definitely comes in the exam. Majority of the years, for instance, since 2019 until at least 2023, there was one question regarding IP. As at least it was a part of a question, IPSLA. Okay. Network operation. We'll see network operations like traffic captures, troubleshooting related tools. Module 5 have 3 subsections. Data encoding formats. Here we'll understand the formats, XML, JSON. 5.2 is we'll see how the automation and scripting works. 5.3 is programmability. We'll see. We're going to talk about the JSON, XML, YAML, and Jinja. Regarding the automation scripting, embedded event manager is there. And guest shell basically in XC router, you create a small container, Linux shell container that you can activate in privilege mode. Why you want to do that? Basically, you can have some script running 24/7 in there, and it can communicate with the router that is hosting that guest shell. So we'll see how to, because one question definitely came regarding this. At least 3 questions will be just for module 5. Cisco is trying to tell you, okay, this is generalized these days to have a knowledge of network automation. Programmability, we'll see how to interact with the vManage API or Manager API using Python or using Postman. Okay, we'll see how do you find out which endpoint to communicate with. Monitoring endpoint is there, configuration endpoint. These are just like a door. If somebody wants to know the list of devices, they should request using API to that door only. So that's basically telling you if you want to find out monitoring, if you want to find out about stuff about monitoring, you will be communicating with that endpoint. So like that. Okay. Similarly, using API, we'll be interacting with DNS Center, okay, or Catalyst Center these days. Using obviously Python, we'll try it with the Postman also. Okay, we will see gRPC, like model-driven programmability. That was the syllabus overview. All in all, 5 modules. Pretty much all of them are kind of important. But you should specifically focus on things that are only mentioned in the blueprint. Don't go above and beyond while preparing, because obviously you guys are working professionally. You're not going to have that much time anyway. Regarding the lab exam, in order to actually sit in the lab exam, you have to have the NCORE passed. It acts like an eligible exam or core exam for your practical lab exam. You can take it anywhere, Pearson View Center. You can take it at home as well. Roughly it's 2 hours of lab exam. And all the questions generally are multiple choice questions, or drag and drop are also there, or connect the boxes which meets on both sides. Yeah, this is going to be web-based content. There is not going to be any documentation access to you available as well. What does that mean? Well, if you start the exam, you can't go anywhere until anywhere, as in that desk, you can't go anywhere. You can't switch the tabs. Okay. You're not going to have, and you don't have to wait longer to get the results. Immediately after submission, majority of the time, you'll find out what you haven't scored, either failed or passed. But practical exam is really, really different. You have to book the lab exam at a specific Cisco locations. Definitely Dubai Center is not open these days. And you have to go to Cisco's portal to find out which locations are available. In that location, you can't simply find out any, you can't simply say, I want to write the exam tomorrow. That happens, less likely to be happening. But what I'm saying is you don't get seats that easily. And if you get it, and even if you book your exam and you try to cancel it, they have changed the policy. At least 2 years back, what used to happen is you would book the exam, you wouldn't get paid, you wouldn't get charged. Okay, you don't have to pay any money until certain amount of days you have left for the exam. They will ask you to pay at that time. Okay, they will ask you to pay at that time. Right now, they are simply cutting roughly 50% of the fees. So in order to find out, it was 90 days before, but I'm not sure if it's 90 days now, Mahendra. You might want to check what they have actually changed these days, just to make sure. If this whole exam is going to be about 8 hours, even in that, you don't have full 8 hours for the lab exam. Just because they have divided it into two different sections. You have something called design, and then you have something called do. Okay, so design is like, it's an MCQ, simple as that. Majority of the people are failing in the design. Design. This, you would say this is funny because that's not hard. The hard is what? The lab is hard. It's tough. You can practice all you want, but if design is and what's funny is you have roughly 30 to 40 questions, not more than that. But the intensity of each question is at the CCI level, and it's kind of a story-based questions. You will get to see, you're definitely going to have a question, obviously, but a resource will be unlocked in separate panel related to that question, and that resource might be a screenshot of certain people talking, like communication between network engineer or staff, maybe a manager and a network engineer. They might be asking about some stuff. Somebody have messed up and they're asking, hey, I did this, what I should do, switch is blinking, something like that. So it's going to be kind of a story based. The tough part here is not is that is MCQ or story based. The tough part is many of the answers will be like, you'll see that only one of them is going to be correct, but you'll be confused whether it's A or B. Definitely you can figure out it's definitely not the C and D, but I think I went too ahead. You can figure it out. It's not C and D, but is it A or B? Because those two options are too similar. That's why people fail. Anyway, you have options to you have option available for Cisco documentation. Definitely, internet is not going to work, but you can explore Cisco's website while writing the exam, while this 8 hours is being taken. If you don't know something, because majority of the people know 99% of the stuff, but for what that 1% of the stuff you got stuck, you should be able to know how to find the documentation for each. And this is something that you have to practice because time is of the essence in the exam. The whole exam, the 8 hours of exam is basically a life cycle. Okay, it's kind of, before 2019 it was much different. I would say right now it's much easier because people are able to correlate. In the design section, all the questions they will be asking, you'll see in the do section, deploy, operate, optimize. This is basically your 5 hours of lab. Many of questions were kind of a fundamental to what you are seeing in the lab. You will see that earlier questions are kind of, they will tell you to deploy certain things. Certain things they will tell you to optimize. Some things are there into, they're telling you to troubleshoot. So it will be like you are building a fully functional communication from each endpoint to other sites of endpoint. They should be able to communicate with each other. So that's basically what's happening. You're building the whole network in there, and each thing is dependent with each other. Like if question 1 is there, if you don't do this, it may affect question 2 as well. Okay. I'll also talk about how to get over that as well. So this MCQ is of 3 hours, the design. That's the big challenge that we'll focus on, and how do you get over that as well. We'll discuss that also. Do, we're going to refer it as a do, right? Deploy, operate, optimize, as in short. Do is for 5 hours. So that huge configurations, you don't even have the 8 hours. You have basically 5 hours to complete the whole lab. That was the introductory section. Anybody have any questions before we actually get started with the syllabus? Duan is asking, can you discuss about cut score and overall score? For the CCIE lab exam, they did not reveal what is going to be score you should be passing. This is funny with Cisco because when you pass the exam, they hide the score with you. They don't share what you have been scored. And even if you fail the exam, they will not tell you the score, rather tell you how well you did as a percentages in each module. If you want to, I'll show you. Just a moment. Okay. So let me show you what does it look like. Majority of the time, what happens is if you fail by any chance, you will see something like this. They will not disclose how well you have done in the, even in the design section, they wouldn't tell you, what is a certain percentage or a threshold you should be passing the exam in. So this is something that is completely hidden, unlike in the core exam. Anybody else? Okay. So I'll consider that as a yes, and I'll proceed with the syllabus. For the written exam, you don't have to be, there is no validity in fact. You can simply, so Mahendra is asking, what is the validity of the written exam? If I take the written, then attempt the lab but fail, how long will my written result remain valid? 3 years is a standard deadline for that, for any kind of certification. So within 3 hours, if you write the exam today, the core exam, from this day, you'll have to write the lab exam within 3 hours, 3 years. So let us proceed. As discussed, I will be talking about the switching campus in today's session, module 1.1. Okay, let us begin. So in switching campus, in today's session, we will be talking about the spanning tree protocol. We'll talk about the PVST plus, Rapid-PVST plus, and MST, and their convergence as well. That will be the main focus. The manipulation of spanning tree, all the features, so where you are changing the priorities, port priority, switch priority, manipulating as per the business needs. We'll also consider those scenarios in the practical as well. So let us start with general PVST. So basically, spanning tree helps you to create a loop tree topology in your switch network. Okay. So back in the days, to avoid any kind of a single point of failures, we started adding redundancies in the network. Rick is asking, configurations will be aligned with best practices. Would you elaborate your question, Rick? So to avoid single point of failure, what we did, we started adding redundancies, because this is a bad sign. If this link goes down, all the devices that are connected to this switch will lose the connection on this side. That's bad. So what we did, we started adding redundancies in our network, double link between switches. Basically example. Let us look at this example. So when PCA sends, let's suppose ARP request, switch A will forward this broadcast. Except this interface, it will forward this broadcast to all the exit interfaces, other interfaces. We are looking at the switch B now. Now switch B received this interface, excuse me, switch B have received this frame on this side. You just talk about this frame, except this source interface, it will send it to this interface, other interface, but also this interface as well. So this basically frame came back to the switch A. But at the same time, the other frame that was sent on this interface accept this interface, switch B have sent it to all the other interfaces. So this also frame came back again. Yes. We will consider all the topics. If you understand the use cases, you'll be able to understand how the syllabus have been, or how the slides have been prepared. Okay, and if you have a specific question regarding those best practices, you can ask me at that specific point. So the first thing that's happening here in this case is that we have a loop, a plain loop, because that frame that was sent back here, both frame that was sent back here, it will also be considered the same way, because it's not tagged saying that was the same frame that came back to me. It's going to treat it as any other frame it was treating before. So that way, so it's just like going to be a lot of frames in few seconds, and we have a big loop. Few other problems are also going to occur here. First of all, each frame that was sent as a duplicate will be sent out to computer B. So multiple frames are being sent. So all those R broadcasts are being sent to computer B. Same thing, the frames that were coming back to switch switch A, is also being sent out back to the computer A as well. It's a bad news, right? This is a problem because the frames do not have a fields like TTL. This is inside of a IP header, which tells us how far the packet can go. And after that number gets to 0, the packet will be dropped, or it simply dies. Frame doesn't have that. Frame can keep on looping forever and ever. Because of this, and as you can see, those frames were doubling down the second. Because of that, the switch may crash. So to break the loop, we have to either remove the cable, shut down the device, all sort of things we have to do. The same story happens. This was with the ARPs. The same story happened with the unknown unicast traffic as well. So to avoid this problem here, this was like the most simple example I've given you of the small loop. The spanning tree is going to block one of the interfaces to break that loop. But this is a final, I would say, final result. That's we have a loop-free topology. But this, how do they get to this process? How do they decide that they have to block this interface? Now let's just understand that in detail, kind of a quick overview. So we have a simple setup here, a really famous one. 3 switches are connected to each other. Switch A, switch B, and switch C. In spanning tree, they have some, in their language, they have something called priorities. All of their priorities, by default, they have a 32768. Well, what is it? We'll get to that again. Just consider something, some kind of a number or ID they have. All of them, they have the same. To make it easier to understand, they have considered their MAC addresses. So switch A have a MAC address of AAA, switch B have a MAC address of BBB, switch C have a MAC address of CCC. Switches that runs the STP, again, this is something that you don't have to enable. STP is going to be enabled by default. And those switches that runs the STP, they exchange the BPDU message as soon as they come online. These are breach protocol. The PDUs, you know the PDUs, right? You know the PDUs. So these are the PDUs, but this is spatialized spanning tree PDUs. That's what they call as the BPDUs. There are going to be 2 types of BPDUs you will see. There's going to be configuration BPDU. Now, what is configuration BPDU? Just treat them whatever I'm saying right now in this specific slide, just treat it as a theoretical point that you have to remember. Two type of BPDUs. One is configuration BPDU, where each switch, as soon as it puts up, it starts sending out all on enable interfaces that are up, connected interfaces to other switches. So this is a generalized message of BPDU that they have to send. We will again look at it, what is inside and how they use it. Other one is a specialized use case, a topology change notification. Some kind of a event occurred. Because of that, they use this second type of BPDU. Because these two types will dictate how the convergence of the general span tree happens. In the BPDU, you will see the bridge IDs are advertised. The bridge ID is an 8-byte field, which is going to consist of two things. The priority, again, it's a number that can be from 0 to all the way 65,000, but by default is 32,768. And it's secondly a MAC address. This is a MAC address that comes from the module as a whole of the switch. Okay, it's not the MAC address of any specific interfaces. It represents the whole bridge, and it depends on the platform, and it cannot be changed again. MAC address cannot be changed, even though priority can be changed. So bridge ID. Okay, the very first thing that they do is they elect a root bridge. The first fact that I told you, that everyone here is started sending the BPDUs to each other, and in that BPDU, they have the bridge ID of their own. In that BPDU, they have the bridge ID of their own. So here, switch A is sending a BPDU. Just a moment, guys. Switch A is sending a BPDU. Switch B also sending a BPDU. And in those BPDUs, they will have two things: the priority plus the MAC address. In the beginning, what happens, in that BPDU, they also have a separate field. This is for their local, what is their own bridge ID. Again, what is bridge ID? It is a priority and the MAC address. In this field, in this local field of that BPDU message, what they're sending each other, they will have their priority, the default priority, and the MAC address. But also they will have a secondary field for the root bridge ID. This is local bridge ID. Second field will be for the root bridge ID. In that also, they will consider themselves as a root bridge. This is part of the process where they eventually block the interface. But first thing first, in this spanning tree domain, somebody have to be elected as a root bridge. How do they elect the root bridge? So since everyone is receiving everyone's BPDU, they now know who has the lowest priority. Since everyone has the same priority here in this case, eventually they will move on to the tiebreaker, which is the lowest MAC address. Here the MAC address is AAA. Switch A have the lowest MAC address. Immediately, both guys, switch B and C, is also going to say, hey, you know what, we found our bridge. And what they do, whatever the messages they were sending just a moment ago, they change this field, root bridge ID. In this field, they will say, okay, we have a new king and its priority is 32768, its MAC address is AAA. So this is eventually they're going to be their BPDU, their version of BPDU. Cool. The second thing is, right after making sure that this root is elected, all the interfaces are the roots. All the interfaces of the root is going to be put into something called designated ports. Think of it like a port that is pointing towards a downstream. Hey, I'm the king, I'm sitting at the top. And this specific interface, designated, is pointing to someone that is sitting at the bottom of me, because I'm considered at the top. Literally, that's the analogy. So root says, I'm the king, I'm not supposed to block any interfaces. And that's what it does. It put all the interfaces into designated. So designated is a role, and it always into forwarding. FWD, okay, it's not P. Consider that. So this is one thing that root bridge does in the step number 2. Step number 3 is for non-root bridges. Non-root bridges have to find the closest interface to the root bridge. Now, closest in the language of the spanning tree. And once they find that closest interface, just like we had a designated port, right? I'm talking about the non-root switches, which is B and C. So they have two possibilities, this and this. Once they find out that closest interface, they will select this interface as a root port. Root port is always into forwarding. Step number 4. Now we have remaining this link. Switch B and C is going to also have an election. So in spanning tree, the same thing happens what happened with the root. They're going to run an election between each other. Who should be blocking the interface in this remaining link? First of all, they will compare their priority, which is again the same. So, sorry about that. And then they will consider, if that's the same, the tiebreaker is going to be the MAC address. And the MAC address, switch B have the lower MAC address, it will say, hey, you know what, I will put my interface into D. So, and you should put your interfaces into non-designated port. Non-designated port in Cisco, you will see something like this, BLK or blocking. So in 4th step, the topology have converged. We understood the criteria that we require to run the election of the root bridge, the selection of the root bridge. For the root port, though, the cost is something that is considered. The first, there are certain other things as well, because in a situation where you have multiple links but the cost is same, other things are also considered until there is a tiebreaker. We will talk about it in a moment. So root port is elected using a cost. The cost is a number that is defined based on it is a fixated number that doesn't change, based on the speed of the link. The idea was to give more preference if a link have higher bandwidth interfaces, faster interfaces. So faster the interface, the lower the cost. The problem here was the number that you're seeing here is what we call a short mode path cost. This is something that is default. You will see on all the gigabit links, you will see for majority of the time. Because the cost could not go lower than 1 when we had interfaces higher than 20 Gbps interfaces. So the problem here was, let's assume if this was, let's say, 40 Gbps interface and this was 20 Gbps, switch B is going to think this, if I go from here to the root, it's still 1 as a cost for this local interface. If I go from here, it's still going to be the 1. It's a problem. It's not able to accommodate the cost here is not able to accommodate higher bandwidth interfaces. The solution was to consider something called long mode cost. Like we talked about the suboptimal routing, because it's not able to differentiate between higher interface and small lower bandwidth interfaces. So another method was the long mode cost. It is 32-bit value. Short mode was 16-bit value. This can accommodate higher bandwidth interfaces. As you can see, it has a support until 10 Tbps in the spanning tree. But if you're enabling this, you want to make sure that you enable it on pretty much everywhere. Otherwise, you're going to have something called suboptimal I will say switching. So this is a short mode cost, and this is the long mode cost. You can see the difference. After 20 Gbps, here is only 1, 1, 1. So how it actually works? We understood that the root was sending its BPDU. We understood there is a local ID. There is some who is the root, its own ID as well. And then there is a third field called cost. This is the format of the frame. It's not something that only root does. This is a default format of the configuration, the first step of BPDU. Root says that's me. Route ID and local ID is going to be the same here in this case. Cost is going to be 0. So when the cost is sent here, it's going to be 0. Switch B have to calculate what is the local interface cost that we are receiving a BPDU from here. The local interface cost, if it is, let's assume gigabit interface, then it's going to be 4. 4 plus 0 is going to be 4 if we go from here. Switch C also in this case have its own version of BPDU that it is sending, excuse me, here in the beginning, because this is non-designated port. Here in the step number 3, this is happening. Okay. Step number 3, what is going to happen? Switch C also will have its own version of it, in which the local bridge ID is going to be CCC, the root is going to be AAA. It will also have selected its own root port, and the cost is going to be 4. The cost is going to be 4. This version of BPDU, it sends it towards other interfaces. It's going to send it here. So switch B is going to treat it as an alternate path. It's going to say, okay, I'm receiving one more BPDU from the other side, and that BPDU have a cost of 4. And what is the local interface is 1 gigabit, and the 4 plus what is shown in the BPDU is 4 is equal to 8. So then it has to be comparing two options. If I go from here, the cost is going to be 4. If I go from here, the cost is going to be 4 plus 4 is going to be 8. The lower is preferred, and hence this became the root port here. This is how the format looks like. This is a root identifier. This is root path cost. This is a local bridge identifier. BPDU type will tell you if it's a configuration BPDU or if it's a TCN topology change notification BPDU. We will dive deep into it, how exactly actually it's supposed to work later. We're talking about only configuration BPDU in here. So their version of BPDU, once it is ready, once they have selected root port, each switch is going to insert the cost in this field here. So this switch is going to say, my cost to reach our king, our root, is 4, and this is advertised to its all designated ports. And it always flows from the root bridge to downwards, from designated port, and it's always received on a root port. Always remember that. Unless it's a topology change. BPDU never flows from downwards to upstream in the PVST. It flows from a designated port. It is always received on a root port. One more example of cost here. In this specific example, we have, look at this, we have switch B and C, inserted a couple of more switches here, D and E. The topology have been converged. We're trying to find out why this switch C have selected this interface as a root port. So basically the traffic, actual data traffic will flow in this direction like this. Why not this? Because in their language, what is better interface which has a lower cost, and the lower cost means that interface have a higher bandwidth interface. This is 10 Mbps. So from here the cost was 100. This is 100. Cost was 19. It sent its BPDU, generated its BPDU, and it is sent towards switch D. Switch D have received a BPDU with a 19 plus its local interface 1000 Mbps. 1 gig is 4. So from D, it has selected this interface that has a cost of 23. And it's going to advertise a BPDU of its own with a cost of 23. Switch C have two options now. This interface or this. One have a cost of 3. Somebody sending me a BPDU with a cost of 3. And somebody sending me a BPDU with a cost of 0. But I also have to add my own local link as well. So let's add my local link to the switch that is sending me that BPDU. 23 plus 1000 Mbps. So it's going to be 4. From here, it's going to be 27. 0 plus, this is a 10 MB. The cost is going to be 100. Okay. What happened? Understood why switch C have selected this interface as a root port. Everybody following me so far? Everybody? Any questions? Okay, cool. Because guys, spanning tree was, for me at least, it was most complicated topic when I actually started. Why networking has to be so tough? I used to think. But studying this way, it was to this day I don't have to study this much to whenever I need to teach, because it's the way we study, right? So what I want you to understand right now, anywhere where you see, you should understand why a certain switch have selected this interface as a root port, because this is the first step of troubleshooting the spanning tree. The switches only make decisions on the BPDUs that they receive. Received BPDUs plus the local, received BPDUs plus the local cost. Have I talked about this? What if the cost is same? In this example,
Isaac, can you hear me?
both. Yes.
Sorry,
Shall I go back?
for interrupting. I'm confused about the election of on a segment between two switches, the selection of the designated switch or designated port.
Mm-hmm.
You said that on a segment we look at the lowest priority, lowest bridge ID.
Mm-hmm.
What does that?
The bridge ID is every bridge ID, the local bridge ID consists of two things. It's going to be the priority, and then it's going to have the MAC address.
Yeah.
I want you to create a question out of this, and I'll explain why that happened. Ask me something out of this topology regarding what question you had. Hello, Hassan, go on.
Yes, sorry.
I'm saying, ask me from this topology. Can you ask me the question that you were asking? But reference this topology so that I can explain a little better.
Yeah, absolutely. So if we take, if the root bridge is the one switch A, I understand that all the ports on the root are designated, right?
Yes,
this
sir.
one is understood. Then if I look at the segment between switch A and switch B, right? The root is this root port. Now between switch B and switch D.
Okay.
So we have here, do we have something, the selection or the election of a designated bridge?
But here's the thing:
Yeah,
you are jumping to the stage 4, stage 3 always in the whole spanning tree domain. Everyone have to select the root port first. Root port. Okay, ask
okay.
that because that will dictate where is going to be the blocking segment. Understood?
Yeah,
Here's the thing: switch B and D. Let's talk about the perspective of D here. Why this guy
yeah,
have become the designated port, first of all. But
yeah,
before that, let's understand what was happening. Switch D
yeah,
received 3 version of BPDUs.
yeah.
Okay, it received one from switch B. It received one from switch C. It received one BPDU from switch E at the time of conversion. And
Yes.
what happened? The first conversion that was the first BPDU that was received from switch B had, look at the cost. They're looking at the cost at the moment. The cost here is 100 MB, right? So switch B sent a BPDU and saying, hey, you know what? From me, the road bridge is 19 away, some 19 some away. You there? Okay.
Yeah, yes, yes, I'm following. I'm following.
Okay. Switch C. Switch C also sent the BPDU and it said it is 100 cost away from me. Switch E also sent it 100 plus this 100. It's a 200 away from me. I mean 200. Switch D at the moment, it's not worrying about the step 4. It's going to worry about, hey, where is my root port? It's going to select the
Uh-huh.
lowest of them all. It's going to say
Yeah.
root port. This is the root port. Immediately, if this is root port, it is saying the goal of all this is to find the closest interface towards the root bridge. The traffic always move towards the root bridge, not PPDU. I'm talking about the data traffic always have to go up. That is the logic, the general
Yes.
logic.
Yes.
If this is the root port, can this guy block the interface? How will we go up if this become the root port, right?
Yeah. Okay.
So everybody guys, and my question is, if I select, because this is my root port, I've selected this, can this guy block this interface? Because then I will not be able to, if this become blocked, then I can't send a traffic towards the root page, right?
Yeah,
I can't.
but switch B doesn't know that switch D has chosen this port as the root port.
Well, okay, Rick, can you can speak, I'm saying. I'm not able to
Okay,
read that much.
yeah, quite basically, yeah, steps 1 and 2 using the MAC address and the priority, yeah, is used to decide who's going to become the root bridge. Yeah, once that election has taken place, yeah, then we are using the cost, yeah, to decide which interface, yeah, we're going to use to reach the root.
Yes.
And this is based on, yeah, the cost is an important factor because it's based on the media that is being used, whether it's 10 megabit link, 100 MB link, or 1 gig, 10 gig, for example. They've all got their own individual cost values, and these need to be taken into account to decide which is your exiting interface to reach the root.
Correct.
Yeah.
Okay, and I'll add a little bit into that. Anyway, I'll continue where I left off. What I'm saying is, once this guy have selected its root port, this guy has selected its root port. Okay, I mean, now these devices are going to be running the election where which segment should be blocking the interface. Okay, always understand, if one segment is root port, the other is always a designated port. It's never ever non-designated port. Understood, Hassan?
That is, I understand, but what I don't understand is how the switch B knows that the switch D has its root port on this segment. Is it because the switch B and switch D, they have kind of election on this segment?
No, there is no election for finding out you are designated and I'm not. I'm root port here. That happens in the fourth step.
I think it's because of the path that they are selecting this as a root port from switch D to switch B. The other path, if you can you hear me?
Yes.
Yeah, we are hearing you.
Yeah, so the other path, it has more cost from switch B towards switch C and then towards switch A.
Anyone would like to add?
Was I right or it was wrong?
But also take into account that switch C has a 10 MB link towards the root.
Yeah, that's
Yeah.
right.
The switch B has a 100 MB link to the root, yeah, and they will have different cost values, yeah, and that's also a key factor in this election process.
Yeah, that's the main reason actually.
Okay.
The Hassan is asking one specific question, is that how does switch D knows, excuse me, I think I spoke opposite of what you asked. Hassan asked here, how does switch B knows that this interface goes towards someone else's root port?
Yeah, I mean, because it can be in designated or it can be blocking. Yeah, so
No, it can't be blocking at all.
yeah, but I know exactly. This is my question: is that
That
how
what you're
how
saying
it
is a
goes
common
into-
sense.
Yeah.
That what you're saying is common sense. But the technical question is, how does this guy knows about it? I'm certain I know about it, but I don't want to say something wrong. It's inside of these BPDUs. Okay, it's inside of the BPDUs. When we'll get to the lab part, we will address this question. Is that okay?
Yeah, perfect. Yeah,
What
absolutely.
I know is that the other side doesn't have any idea that it's just
Yeah,
it's what you're saying actually doesn't even happen, what I know. Okay.
yeah,
Switch B doesn't say that you are root port, or switch D doesn't say to switch B that you are designated port. It's part of the election, and until the switch, when we'll get to the what do you say, the practice. Well, let's try it out.
okay, yeah. Thank you.
But that was a good question. But what if is the cost same? Right? We understood the lower cost is the root interface, root port. But in cases like this, where if this is a switch A and this is switch B, and both interfaces are sending the root BPDUs, each having the cost of 0, and local interface will have a cost of 4. That means the total cost on both sides is going to be 4. The cost is same. How do you find out? And without root port, you will not move forward. That's the second step. Means obviously third step, because these guys are going to be DPs, designated ports. They consider the switch that is having the lower bridge ID. This doesn't apply here because the sender is also the same. Consider this in this example. You have a switch A here. This is switch B and switch C. And this is, let's assume, switch D. In this case, it applies. Switch D receiving 2 BPDUs with a cost of 4. Total cost on both interfaces is total of 8. In this case, switch D have to decide which is a root port, but the cost is same. At this moment, it's going to compare what? The BPDUs that is receiving on both interfaces is going to look at their BPDUs. In that, it's going to look at what is sender's bridge ID, not the root bridge ID, but their bridge IDs. Obviously, these guys should win election considering their priority is the same, because bridge ID is compared of two things, the priority and the MAC address as well. And then it will decide this should be the root port. And then these two guys will be running the election. This guy will be running the election to who's going to block the interfaces. And again, they're going to compare the same thing, priority and MAC. But in cases like this, the second criteria applies. We'll prefer a lower sender bridge ID, and the interface that we are receiving that lower sender's bridge ID, we will consider that interface as a root port. Go on. Okay, I thought somebody asked the question. So that's why in this case, the second criteria applies. But if that is the same, then we move to the next step. What is the next step? We will consider, because here in this case, the sender is also the same. The cost is same, the sender is same. The root port needs to be elected. We will select the port with the port priority, lower port priority. What happens is whenever a BPDU is sent out on both interfaces, by default, port priority will be 128. Both interfaces, both BPDUs will have a priority created and priority inserted in the BPDU. The receiving switch, a non-root bridge, is going to receive it, and it will treat the root port which has a lower port priority in that message. But if that is the same, then the ultimate tiebreaker is going to be the lower port ID, and that's why /20 0/23 is going to become the root port, and this will be definitely blocked because obviously I will put the interface into designated port. Obviously, I will put this interface as a designated port. So I will not block the interface. King never bows, right? So what Cisco even does, they combine the priority and the port ID. So for instance, if FA0/24 or FA0/1, this is the first interface. So ID is going to be 1. So first interface ID is going to be 1. 128.1 is going to be something that will be in the you'll be seeing in the show spanning tree output. Hopefully it's clear how does the root port is elected. At least that is clear. The cost, then if that's the same, we will prefer the lower sender bridge ID. That is also the same. We will prefer the lower sender port priority. That is the same. We will consider lower sender port ID. But in Cisco, it is shown combined, the third and fourth.
It will
Yes, please, Jay.
yeah, it will compare between these two interfaces only, no? The 023 and 025, correct?
Yes. Or more, you should be saying it will compare the interfaces that is receiving the BPDUs.
Okay, yes, the receiving interface.
These are the receiving interfaces. This is our root already elected.
Yes.
This guy was
all
sending the
report
BPDU.
in
Yes.
DP state only.
Yes.
I was having one question. Can we go back in the previous slides? That there we will have, yeah, correct, this one only. My question was like the cost that you're saying that for each port. So far I have understood in this slide, like in this slide we are just talking about the like the shortest path for the reaching the root bridge, correct? That will be elected as a root port, correct?
Yes, sir.
Yeah, so A switch, B switch, C switch, D and switch E. So each switch will be like checking the shortest path to reach the root bridge. That interface will be like considered as a root port. Okay, so that's first thing I understand this thing. I just want to know one thing, that the cost you were saying, like the switch D, like the switch D will receive cost from root bridge. So
Switch
that is a sorry.
this guy, right? Switch B.
Yeah. Yeah, switch B will receive cost from root bridge. That is the cost is 19. And same cost will be
Mm,
advertised in the downward direction, correct?
No, 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 no. BPDU contains the cost
Mhm.
from the sender's perspective, how far the cost is. It is, this is itself, right? That's me. How far away me from myself? 0.
Yeah.
Does that make sense? So the
Correct.
BPDU is always, the route always sends out to every interface has a poor cost of 0.
Okay.
And these guys, they are receiving cost of 0. How does switch B said 19?
Yeah.
Why is it 19? It's not because of the BPDU received. They take, this is the BPDU received cost, okay? Then they will consider the local interface cost. They will combine it with it.
Okay,
And
that is like towards root.
yeah, and even if it has 100 interface now, Vijay, it's going to compare it with everyone. Every interface it will do that. What it's going to do, it will say, okay, I'm receiving BPDUs from 100 interface. I will take those BPDUs, the cost inside of those BPDUs and the local interface. Local interface here is an
19.
interface with 100 Mbps. So the cost is going to be 19. So 0 plus 19 is total of 19. Does that make sense how it works?
Correct. Correct. And then it will same thing. It will like share in the like downwards that my cost is to reaching the root. It's 19. Correct.
And yeah, so speed sends it the BPDU and says the route is 19 away from me.
Okay.
The route is 19 away from me. Switch D receives it. Somebody is also sending them. So from the perspective of switch D only, we consider this example, right? And here we said, I think it was 200, right? Anyway, switch D said, I received a BPDU with the cost of 19. I received one BPDU from here with a cost of
The
100
cost of 100 and 104.
plus 19.
4. 100 and plus 4. 100.
This is 10. So this was basically from here 100, 1019, 119. Look at this 10 Mbps. No, yes, you're right, guys. 10, 100. So switch C sent a BPDU with the cost of 100. Am I right, guys?
0 plus 100.
0 plus 100, so 100.
And then
So
switch D will add is local interface cost.
no, yeah. So from if I go from here, 100 plus this 1000 Mbps is going to be 19. So in this case, is going to be 119.
1000, I think 1 GB was 4, I think.
This is 1 GB, right? Yeah, okay. And it doesn't matter. Anyways.
Yeah,
104. Let's say 104. Switch C, switch E, this guy. So total from here, we'll get to the point here. Okay. So from here, if we go from here, the total cost was getting to 200. Let's assume that. We'll definitely select the interface that have a lowest of all. Okay.
But one more question here. So switch C will send the same thing at the both side of interfaces. The interface is connected to switch D and interface connected to switch E. Correct?
Can you repeat your question, please? Switch C.
So switch C like will send the BPDU in the both the directions. This connected towards switch D and connected towards switch E.
It should be sending actually the BPDUs will flow like this. Okay.
See, in the current scenario, like the only like this thing is the election process is going on only. Okay, there is no port is blocked and nothing is no extra designated port is allocated right here. So just now, just switch C is just sending the my cost to reaching the the root bridge is this thing, the 100. It is like sharing the BPDU downwards. And the, like it, my question is, it will send in the both the directions. We switch towards switch E as well.
It
The
will
same
do
thing.
everywhere. In the beginning, it will do everywhere. First of all, what happened here, we're going to assume here, this was its root port. Only then it was able to do that. Otherwise, it wouldn't do it. You got my point? So BPDU have to flow every single time in order to, otherwise, if you connect some high bandwidth interface later, until and unless it will receive this BPDU on this side, it's not going to find out that we have higher bandwidth interface in this network at the moment. Okay. So if we talk from the perspective of the switch C, in the beginning, everyone everywhere sends a BPDU, everywhere, regardless of the interface. Okay, because you talked about before this port were elected, right? So in the beginning, they send it everywhere. Configuration BPDUs. Okay. And here's the thing, Hassan, if I would like to go back to your question, you there? Hello, Hassan, you there? Okay, is he here? I would like to go back to your question. If we just talk about this scenario, the root is thinking from itself. It's not aware of the other side if the other guy have been elected as a root or not. It doesn't matter to it.
Yes.
It's just thinking by itself, for its selfish guy here.
Yeah.
So all it has to do two things. Select a root port. If I talk about this, select a root port and then decide it has to block or put the interface into designated port. Only two things, that's all in the spanning tree.
Yeah.
Okay, I'm thinking of common sense here. Here, so what's going to happen? First of all, when designated port root bridge says, okay, I'm the designated port, definitely I will not put the interface into blocking state. In the beginning, couple of BPDUs were sent out and it knows that these are inferior to me. The guy that is sending me its BPDUs is inferior to me because it has a lower bridge ID.
Yeah.
It will not react. It will keep the interface as a designated port. Same thing happening here. And this is actually we can find out using debug command as well. It will only react in the case where we have it will only react in case where we have a higher superior BPDU. So if switch D sends the initial couple of BPDUs also, this guy is gonna say, hey, you're smaller than me, right? Obviously it is. Switch D is smaller here in the language of spanning tree. So what's going to happen? Switch B will say, I will not react. Do I have to put this interface into root port? I already have a root port, right? Right?
Yeah.
If by any chance, this switch D in the beginning, the couple of BPDUs that it sent, in those BPDUs, if it had a priority of something like 32,000, because priority is preferred first. Switch B it knows that its priority is 32,768. If you say, hey, you know what? I think I found someone that is better than me. Hey, you know what? Let me put this port into non-designated port already. You got my point, Hassan?
Yeah.
Switches this is literally the point that I'm saying here. If they don't have the awareness of a global topology, their decision is relies solely on which port receives the BPDU. Understood?
Yeah.
So based on the BPDUs receiving, it is going to dictate whether it should be putting into designated port or non-designated port. Understood?
Yes.
So did I answer your question correctly? Because it cannot be anything else apart from this. It literally
Yes, I think, yeah.
And you will see I have a couple of slides for moving forward, but I can show you how they are actually deciding these things.
Thank you.
Okay. So this was regarding the cost, guys. I think everybody's clear regarding the cost. How does the cost? And you can manipulate these things to have one interface, because here's the thing, they will only move to the next step when they feel like both are equal. If I go to, let's say, a 0/3, and I said the local cost is 100 of this interface in the spanning tree, immediately 1 is going to be compared with 4 with this 100. This interface will win the election and it will become the root port. And we will get to those scenarios as well, guys. Regarding the convergence, now we are talking about the convergence. How does the convergence happen? And we'll also talk about a couple of features to fasten them up. In spanning tree, interfaces that are just generally in shutdown state that have come up, they go to listening first and then learning. This is to like slow down the pace to avoid all those loops until everything converged. Okay. In these states, the BPDU packets, the BPDU frames are exchanged. If the interface is in the down state or discard state, which is the same thing, it will move to listening and learning. Forward delay is 15 seconds. So it takes roughly 30 seconds until the interface is fully functional to send the traffic, basically, to forwarding. Then there is something called max age. We'll talk in detail what is max age. But if an interface is into non-designated port, NDP, that interface, NDP, that interface is going to be put, first of all, through a max age timer, which is 20 seconds. In this topology, if a switch, shall I go back? In this topology, okay, this is a blocked interface. Something called a direct failure occurred. What does that mean? Switch C have expected something here. It is no longer receiving any BPDUs because that was the sole thing that was keeping me saying my route is alive. Every 2 seconds, the BPDU configuration BPDUs were being sent. As soon as I stopped receiving it, doesn't matter whether the interface is up or not. As soon as I stopped receiving the BPDUs, hey, you know what? Something is wrong. Let me just make sure. I will still consider this interface as a root port until 20 seconds. It is in an age of that root bridge BPDU. Only after 20 seconds, I think still this guy is really down, man. I have to consider this interface now. So it will now do learning and listening thing. So from blocking until the link goes up, it takes roughly 50 seconds. 50 to 52 seconds. It's not fixated to that only. Cool. How do we change the timers in spanning tree? You want to change the hello timer? The command in the global configuration mode, spanning tree, hello time, and whatever the time you want to set. At least 2 seconds is the default one. Max edge is 20 seconds. Forward delay is 15 plus 15. But you can change them in one go. You have to do that. Max edge you can set up at least 6. Spanning tree forward time is 4. This is a forward delay, this one. I went to the switch 6 here and I'm checking. I didn't configure it on switch 6. So switch C. I'm checking the show spanning tree output and I want my output to begin with hello. So what happened here? It's showing me the hello timer, max edge timer that I configured on the root port. So root here in the normal spanning tree is like a king. Whatever it says is the de facto standard everywhere that they are going to listen to it. Here on the root bridge, okay. Was that? Muhammad, you good? Mahmoud? You guys
Yeah.
following this, all right? Huh? If you guys need anything, please do let me know. I'll stop and explain. So show spanning tree is the holy grail of troubleshooting. You'll get everything, or at least majority of the things you want to know about the troubleshooting of your problem. Show spanning tree. This is nothing but a BPDU. The version of the BPDU on your checking. This is which one you're checking this command on now. So it's going to be its own version. It's going to be its version. I told you the cost is going to be 0 because that's a root bridge. you will have in the BPDU, you will have cost, you will have the root bridge ID, right? You will have the local bridge ID. All these things are going to be inside of the BPDU version of that switch. On the switch, look at this. This is the root bridge ID. Root ID priority is what? 32769. By default priority is 32,768. The priority considers the VLAN number ID as well. So we are talking about VLAN 1. Why VLAN? Because we run a version of PVST plus. We will talk about it in coming slides. What is that? We'll talk about its flavors in detail. That's why VLAN 1, 32,768 plus 1 is 32769. That's a priority. This is a MAC address. And it says, hey, you know what? There is no cost because this is the root bridge. I am the root bridge. So this is basically the frames, what you're seeing in the frame. That's all. And these are the timers considered by the root bridge. And then again, even though it's a root bridge, which can change, hey, it can change separately, the bridge ID is also mentioned. Bridge ID is also mentioned here. It's priority, separate, it's set separately here, okay? Bridge ID, address is there, hello time. Now what is this? Aging timer. This is the timer of, on this interface, if we learn any MAC addresses, how long I will consider that MAC address as active and not a stale. After this, if I don't see any MAC address or if I don't see any frame that I have a source address of that MAC address after 300 seconds, there is no activity, I will remove that MAC address and consider it as a stale entry. I will consider it as a stale entry. What else we got? Switch 1 is saying, I have two interfaces, 0/0, 0/1. Both are, role is what? Role is designated port, and both of them are forwarding state. This is not a root cost, this is a local interface cost. 4 and 4. Priority, look at this 128. Because this is the first interface is 1, this is 2. So the BPDU that we are sending towards switch 2 is going to have 128.1 priority, is what telling you. On this side, 128.2 priority. These are the type of interfaces. You will generally see the P2P interfaces as a full duplex interfaces. In older days, you had what do we call it? In older days, we had a sub in between, which was used to run as a a shared link. But this is a P2P link. What these guys are thinking, switch 2 and switch 3? Switch 2 says, okay, we understand this is a VLAN 1. Who's our root? This is root ID is 32769. Someone with the priority of, which is the same as me, but okay, this was the winning criteria. Somebody with a MAC address of this is the root, and from my perspective, switch T's perspective, the cost to that root bridge is 4. How do you find out from here? It's port 1. 1 basically the first interface, which is pointing to the gigabit 0/0. Look at this gigabit Ethernet 0/0. These are the timers, what is conveyed by switch 1 in that BPDU. And this is my local bridge ID. In this example, just try to see that this is only the difference between. That's how we can say that switch 1 had a lower bridge ID. That's why it became the root. Something cool is happening here. We will talk about it here. Generally, the 300 seconds is what it's supposed to be, but because of the something called topology change, aging time was 15 seconds. We will talk about it in coming slides. Logically speaking, gigabit 0/0. That is my root port. The role as a root port, and this is the forwarding. This is in the forwarding. This is the local cost. The local cost is 4, and which is considered and shown in the BPDU. The priority of the local interface local interface priority, okay? Local interface. And link is P2P. What else do we have? We have gigabit 0/3, which is also shown here, designated. So an interface either will be in root port or designated port. That is what they consider eventually. Somebody else sent them uh, a BPDU. And they're saying from them, the cost is 4. From them, the cost to reach the root bridge is 4. Well, I also have root port. Are they in this link, which I'm receiving this BPDU, do they have a better BPDU than me? Hey, no, I will immediately put this interface into designated port. On the switch 3 side, what they're saying, pretty much the same stuff. Okay, switch 1 is my king. This is the cost. The root port is 2, gigabit 0/2 is the second port in that switch. That's why it's saying port number 2, and it is also telling you which interface that it is. At the same time, switch 2 is also continuously, every 2 seconds, is sending the configuration BPDU. This is literally the BPDU that is sending to switch 3. It's saying, I found my root port. I found my root port. This interface, can I put into the designated port? Hey, I'm receiving a better BPDU. Superior, they call it a superior, literally in the debug messages. I received the superior BPDU on this interface. So this will not be root port, definitely, because I already have one. I lost the election here because on the other hand, on the other side, I have a better superior switch sitting in there. So I will consider my interface as a alternate. This is for us to understand. This is considered as a non-designated port. In the Cisco, they call it an alternate port, and this never is in the forwarding. This is a blocking port. It's not going to send anything here. It's just simply going to listen on this interface. So the BPDUs will always flow in this direction like this here, because from root port to designated, excuse me, guys, from designated port to root port. Root port is where you receive the BPDUs. And this guy is going to send the BPDUs like this continuously every 2 seconds. And these guys are going to send continuously, you receive this BPDU every 2 seconds. And this function of receiving BPDUs every 2 seconds is what will keep the span tree convergence alive. If you stop receiving here, it will consider after some time that my root is lost. If you stop receiving the BPDU on this side, it will think that, okay, there is no loop anymore. I have to remove this interface, because this happens in situations where you have multi-mode fibers. There is no, I stop receiving the BPDUs, I will remove the blockage from that interface. This happens. Here it was simple. Why did switch 1 became the root bridge? Everyone had the same priority. Every switch had the same priority. The lowest MAC address among all 3 was the switch 1. Exactly, that's why it became the root bridge. But why did switch 3 had to block the interfaces? Now switch 2 and 3, both of them were sending each other BPDUs. Immediately, they don't tell anyone, they simply decide based on what they have of themselves and what they're receiving. In this time, switch 3 knew about its own MAC address and priority. Priority is the same, so let's compare the MAC address. Switch 3 aware of its own MAC address, priority is the same, let's compare the MAC address. Both knew, I'm not going to block the interface, I will block the interface. Now, you can change the priority, because the priority is what changing the topology. If you leave anything to God's plan, it's going to be a regrettable situation in the future. Hopefully not. But everything in here was decided based on the MAC addresses. You have some rookie guy, a new network engineer joined, and that was the first day. He connected as old switch. Old switches have an older MAC address. Let's assume that, or some leftover configuration have a priority of something like 4096. Immediately, the topology traffic will flow like this in this direction. You will see you're going to have a lot of problem. To avoid these things, we manually set the root priority. If I'm certain that the switch 1 is always going to be the root, there are two ways I can set up the root priority, because priority is the first thing that I will compare before going to the MAC address. Only in the time where it's the same everywhere, I will consider MAC address. There are two ways. First method is you can simply use a keyword called primary. Spanning tree, VLAN 1, because you're running a version of a spanning tree where you have different instances. That's why you have to define VLANs here. We will talk about in detail again, but we're getting there. Spanning tree VLAN 1, we're saying root is going to be primary. What happens here is that if the priority is set to 32768, which is default, it will drop down to 24,000 some change. If the root priority is below 24,000, it will switch itself to 4096. This is something that is dynamically selected, but selecting primary. You also have an option here of root secondary as well, because the second switch here is aware, the second guy here is aware of the root priority, the priority of the root bridge. It will keep higher priority than available root priority of that bridge. But if you want to have a little bit more control, instead of dynamic, you can set the priority manually as well. It's going to be remaining to that value regardless of what you set. But you can't set like 1, 2, 3. You have only, you can set either 0 or increment of 4096. That's why the value is like a random number as a default value, something like 32,000. Spanning tree, VLAN 1 priority, if you set 0, this is going to be 0 plus 1. For VLAN 1, the priority of this switch is going to be 1. On switch 3, the same topology, I came here and said spanning tree VLAN 1 root primary. Root is primary. Immediately, first of all, the priority was 32,000 earlier slides. Right now, what you're seeing, switch 3 is saying in the show spanning tree output that this is the root bridge. I am the root bridge. And the priority is 24,000. Immediately, topology changed. And you see, since I changed very recently, I changed the topology and I checked the command, you will see that nowhere we have root port. The port that was in gigabit 0/3 was, you can see that it is into listening port. So it's basically changed, it removed its blocking state. Interestingly enough. So you see, it's very quick and the change happened. And now these guys are going to think we have to find the closest interface toward that page. We're looking at influencing the root port election now, because every non-root switch in this case, even in this case, they have to find the closest interface to the root bridge. The cost, lowest sender bridge ID, lowest sender port ID, lowest sender port priority and port ID. Here in this case, we will look at in each case, you're trying to influence things. We will look at each scenario. In this case, let's say on switch 3, you know that this interface is a blocking state. But for whatever reason, I want to consider this interface as the root port. I want my traffic to flow in this direction. This guy don't have to do anything. It is already is a designated port and it is sending the BPDUs. It is thinking that its switch 2 is thinking someone is below me, like as in physically kept. On switch 3, we checked here, gigabit 0/3 into blocking state. Okay, indeed. We went to 0/1, this interface, and I increased the cost, spanning tree cost in generally for all the VLAN. On switch 3, what happened? Again, when we checked it, immediately, now it knows that I have an interface that have a cost of 8. It is immediately scanning. And I have an interface that have a cost of 500. Which one is better? Here, just remove the blocking state. This is better. I will keep this interface as a root port. Anyhow, the designated port was sending the BPDU and it will receive on root port. But this guy will block the interface because root bridge obviously is very arrogant here. It's not going to do anything. So this is how you manipulate the cost. But in cases where the cost is same, I'll take the same scenario again. This is, you can't influence. How can you influence the sender's bridge ID? It's something that is fixated in the system. So we're going to move to the next step. We want to change the port priority. The port priority is something that is not the local, but what you receive on the interface. On switch 2, we have a root interface. Look at this. We have a root interface, gigabit 0/2. And I've added one more interface in here. So there are 2 loops, okay? The spanning tree is going to run the same 4-step logic for every loop, not one. So this is going to be one, and this is one more. So they have to find 2 interfaces where they have to block the interfaces. But let's look at this because this is a unique scenario. The cost is same. The sender is also the same. Here, how you're going to manipulate. Here, we will change the port priority on the opposite side because the decision is not based on the local port priority, but rather what you're receiving in the, because priority is part of the BPDU frame. Priority is a part of the BPDU frame. I'll show you. When this guy sends the BPDU on both interfaces, it's going to be on 0/0, it will have 128.1, 0/1 and 0/3 and 0/2. So it's going to be have 128.3 because 0/0, 0/1 and 0/2. So this is 1, this is 2, and this is 3. That's why the 0/2. So BPDU sent from these interfaces will have these BPDUs. Switch 2 is choosing, which is also the same in the earlier case, it's also the same. It is going to prefer the lower interface definitely because it is just 4-step. But I want in this case gigabit 0/2 to become the root port. Otherwise, 0/2 is an alternate or blocking state. We went to 0/2 of the other side here on switch 1, 0/2, and we changed the port priority to 16. Now it's sending. It is sending the BPDU a 16.3. Priority is something that we'll look at first. Switch 2 is going to receive the BPDU. We'll say, hey, cost is same, the sender is same. Then priority, the lower priority I will prefer. 0/2 automatically becomes a root port. Again, we are checking on switch 2. Do not get confused. It will be changed on the switch 1. We are looking at switch 2, so don't get confused here. So what you saw until now was the convergence for the common spanning tree. And this is something that is defined in the 802.1d standards. Cisco says we don't want to run this. Obviously, it's kind of a revolution that happened. We don't prefer to run the PVST, but this is what came earlier, and it was a big thing at that time. Common spanning tree is what we saw until now. Cisco run its modified version. Rather running a same instance for all of the VLAN, Cisco runs separate instances, separate processes for each VLAN. If you have VLAN, that's why VLAN 1 is something that is default data VLAN, and that's why you saw the same. That's why you saw that instance of that VLAN. If you have VLAN 2, it's going to create. Here I had VLAN 1, 10, and 20. You can see show spanning tree summary will tell you just a summary. It will tell you the instances shown here. VLAN 1, 10, 20. You have 3 VLANs and 3 instances running. Out of all of them, which you are the root bridge? Now we're going to talk about it later, the output of this later. But the idea is to tell you the per VLAN spanning tree is what runs on default in Cisco switches. For each VLAN, you will have a separate instance of the spanning tree. So as a summary, what we know until now, the root is elected, the root port is elected, and all the other ports are put into either blocking or designated. That's generally to sum up what happened until now. So after the convergence happens, what we saw until now, there is something called convergence, okay? There is something called reconvergence. Something changed in the topology, then how does that happen? Convergence happen. We are going to take a look at that. Let's establish a couple of things. How does the designated port behave? After convergence, in each link or each segment, only one port forwards the BPDUs, and that port is a designated port. And each segment, you will never see 2 designated ports in each segment. You will see only one designated port. The other guy is going to be either root port or blocking. That's all. There is something called topology change in the spanning tree. In whether it's a common spanning tree or per VLAN spanning tree, which is the same case in Cisco, something called topology change. It's an event. It occurs in a couple of cases. First, when a new root is elected, when a switch becomes a root bridge, on that switch, we can consider a topology change happened. A port moves from learning or forwarding to blocking. On that switch, a topology change happened. A topology change notification BPDU is received by a designated port. Let's go back. I said a TC and BPDU. Until now, those BPDUs that we were discussing was called as a configuration BPDUs. A separate BPDU is called topology change notification BPDU. A very small BPDU in the frame, nothing else is there unless except the name TCA, that's all. No flags, no data, but I want you to understand that if some switch becomes a root, a topology change happened. A port went from blocking to forwarding, a topology change happened. If on a designated port, somebody sends a TCN, because topology change, TCN BPDUs are something that can flow in the opposite direction. That always in the beginning flows the opposite direction for the topology change, so that everyone knows, hey, something happened. Couple of reasons, we'll talk about it in a moment. So let's examine this here. For whatever reason, out of in the list here, that topology change happened on this guy. It, by the law, it has to notify the root. It has to notify the root because the topology change happened. Because it's possible that one interface was blocked earlier, or an interface went from forwarding to blocking. You shouldn't consider me as a pathway. General rule of thumb is that I have to notify. So everyone should update their MAC address table. Why, we'll also explain that. But some reason, out of any reason that I mentioned here, a topology change happened. Immediately, I will send that second, you see this, TCN BPDU. TCN BPDU, the upper switch, the switch that have a DP also triggered the TCN, because the reason number says a topology change, TCN BPDU is received by DP. So this was a designated port that received that BPDU, that received the BPDU, TCN BPDU. So it triggered the topology change. But before it sends it to upstream router, it has to do one thing. The configuration BPDU that it was sending earlier, general configuration BPDU, there will be a flag called topology change acknowledgement. I'm talking about the really important stuff you guys focus on here. When there will be a flag called TCA, topology change acknowledgement, that I will enable, that flag I will turn on. I will, couple of BPDUs that I was sending before, just like before I'm sending now, I will have topology change saying, hey, whatever the topology change you sent me, I receive it. This is my acknowledgement. This is my acknowledgement. So it sends the TCA configuration BPDU. In the configuration BPDU only, the TCN BPDU, TCA acknowledgement flag is set. That's how this switch knows, okay, I don't have to panic now, I've done my part. But also topology change triggered here because of this. It's going to send it towards its root port. Until just like this, everyone sends it to their root port and other switches acknowledge it until it gets to the root bridge. And everyone here going to receive a configuration BPDU, a separate flag set, which is a topology change happen. It's a flag. Don't get confused. What was sent here is a BPDU. This is the first type of BPDU that we were using until now, but in the inside of it, the flag was set now. Until unless anybody sees this, nobody is going to panic. But now what's going to happen? Look at this. What I did here, switch 4 and switch 6. I've added in this older topology, I've connected 2 more switches and connected one link in between. So after adding a link between switch 4 and 6, switch 6 have detected something happened, topology change happened because link went into forwarding. Immediately it is sending onto its root port on switch 3's designated port. It is sending this BPDU. What is inside? Nothing. This is the full version of that frame. It's telling you what type of BPDU it is. That's all. Topology change notification. That is all. Nothing. What does switch 3 does here? Upon receiving the TCN BPDU on gigabit 0/0, again it triggered a TCN. But first of all, I have to send that topology change. Look at this. This is the configuration BPDU. This is how it looks like. Type is configuration. Excuse me. The type is, this is the configuration BPDUs. In that, this is the version of switch 3, which is telling I acknowledge your topology change that you sent me earlier. How we know this is switch 3's version? Look at this. It's telling switch, this is the cost to root bridge. This is the root bridge ID. This is my ID, which is different than switch 1's. So this is the second step. TCA, topology acknowledgement, is been set. Now switch 3 also have a triggered a topology change. It needs to send it towards upstream switch, which is until it gets to the root bridge, and it did get. So root switch here in every interface is going to quickly flood out. Every designated port is going to flood out a normal configuration BPDUs. But it will have something called topology change flag also set. Topology change flag also set. This is a port identifier in hexadecimal, guys. This is what your port priority, This is 800 wins. it is received on first interface, most probably this one. But anyway, upon receiving this, these guys also change the BPDU that they were sending. In that BPDUs, those configuration BPDUs, they are also going to change this flag says, hey, topology change occurred. Everyone is flooding this flag in the BPDU they were sending every 2 seconds. But why? So that everybody changes their aging time of their MAC address table from 300 second to 15 second to 15 second. We will try to understand it by an example of direct link failure and uplink fast. And we will connect back to why do we have to change why all this, why topology change BPDU even have created. Let's understand by direct link failure. On switch 3, the topology is simple. We have gigabit 0/2. This is into blocking state. Simple as that. We have gigabit 0/1 into root port. We have one more interface, 0/0, which is designated interface. This is P2P link, and this is where a PC is connected on switch 3. Simple. Traffic will always flow from here. This interface is into blocking. But now, again, what we are trying to do here, the PC that is connected on here, this VPC, basically this VPC is connected to switch 1 on 0/2, and switch 3 have learned a MAC address. Just try to remember 6874. It is telling here that we have learned this MAC address on the 0/1 on the root port, and that's why, because that's where we learn the MAC address. We will never learn the MAC address here. We learn the MAC address here on the root port. That's why we'll send the traffic on that interface, and that's how the traffic always goes towards the root port. But anyway, what happened is we shut down the interface on 0/1, and switch 3 have lost its root port. We stopped receiving what happened? We stopped receiving the BPDUs from our beloved root switch on the root port. Meanwhile, at the same time, the switch 2 were sending all this time, it was sending its own version of BPDU. So this is packet capture on here. Every 2 seconds it was sending with the cost of 4. And the interface that was sending, look at this is port ID. This is how 808803. This is the third interface that it is sending from on switch 2, gigabit 0/2. 0/0 is first interface, 0/1 is second, gigabit 0/2 is the third interface. Look at this. So that when they send a BPDU, they also include their local port ID as well. This is what it is. The cost from the switch 2 is 4. This is the root bridge. So now on the blocking interface, since we lost our root port, now I did a debug here. Look at this. Debug says immediately, hey, you know what? For VLAN 1, we have heard a new route on gigabit 0/2. The total cost is 8. How? This and this 4. Not immediately, but at least we have to wait until 20 seconds to confirm, because that's max's timer. Max's timer. Then we will change the timer to listening and learning. And on 0/2, we sent the topology change. It is telling generating a topology change trap for port gigabit 0/2. I sent a TCN BPDU on 0/2 on this interface, because now this is my root port, and switch 2 received it. Here's the thing. The problem with this is that if I had something connected here, switch 1 would always send the traffic on this side if this link was gone. But until 300 seconds, which is 5 minutes. But when a TCN was sent, and that TCN was acknowledged, and again one more TCN was sent towards the root bridge, that root bridge sent everyone. That root bridge sent everyone what? The TC and flag set in the configuration BPDU. Until and unless we receive this, we will not change the timer to 15 seconds of the MAC address table aging timer. And when we do that, everyone changes that, including me. And the older entries that were believing the certain host lives here, myself also that was believing that this VPC was living here will be aged out within 15 seconds. Are you guys understanding? Mahendra, Tuan, Mahmood, you guys there?
No, I'm lost a bit.
You lost it? Others?
Yeah, couldn't get it.
Which part didn't get it? Did you at least understand the topology change?
Yeah, I couldn't get it from the start, actually.
Look at this part. You always stop me when you're not able to follow up, because we kind of invest double time going back and so that it will save time. Look at this thing. Don't get confused between a topology change notification BPDU and topology change acknowledgement BPDU and TC and flag. TC and flag. The purpose here, something happened here, okay? The topology change triggered. It has sent a topology change notification. This is the second type of BPDU itself, the second message is sending. Even before this, every 2 seconds, we were receiving the BPDUs like this. But this was the first BPDU, the configuration BPDU. Like this. Upon receiving the second BPDU, second as in second type of BPDU, because the topology change occurred, the upstream switch have, which it was sending the first BPDUs, in that it will enable or set a flag called topology change acknowledgement. It will be set to 1. It will be set to 1. It is indicating I acknowledge what you sent me just now. This behavior will happen until this second type of BPDU gets to the root bridge. And then they will only listen to root bridge. They will only listen to root bridge. And root bridge only have the capacity to the first configuration BPDUs. In that, there will be another flag. This is the flag, not the message. Inside of the first type of message, the topology change flag will be set. As a result, everyone will change their MAC address table aging timer from 300 seconds to 15 seconds. Are you getting now, Mahmood?
Yes, get the idea.
Okay. So there is a TC and BPDU. This is a flag. So this and this, both of them are flag. One flag is using to acknowledge the downstream switch. One is to acknowledge by the root bridge to tell everyone, hey, something happened, please, everyone update their MAC address table. But instead of flushing everything, hey, just gracefully, at least 15 seconds. If you don't receive anything under 15 seconds, just consider those MAC address entries as stale and remove those entries. What happened? Because of this 15 seconds, on switch 3, the 6874 that we had a MAC address table entry was considered on 0/1. But now this interface is gone. This interface is gone. And this interface is something that we have to connect it with. Because of the 15-second MAC address table aging timer, we have removed this entry within 15 seconds. And now, what is the 6874 lives at where? Gigabit 0/2. Are you guys following me? Why do we have to change the timer to 15 seconds? Everyone? Hassan? The Hassan is dropped. Because because of topology change means what? Topology change means, hey, something happened. We don't give a damn about it. We don't give a damn what happened. But if you don't do anything, we may send the traffic to interfaces that is stale, that is down. So the new root port, it sent a BPDU. This is the topology change notification BPDU. It is sent to until it came to the root bridge. Until it came to the root bridge. And root bridge sent everyone, hey, everyone, please change your timer to 15 seconds. Don't wait until 5 minutes. Something happened. We have to update our MAC address tables. And hence, from 0/1 to 0/2, that's how we go in 15 seconds. But still, in today's age, 15 seconds is also too much. So total time of convergence, what happened? How much time? Because this interface was into blocking state. So max edge timer is 20 seconds, learning is 15, listening is 15. Total timer plus 15 seconds to stale for the stale entry. The total convergence here is more than 15, is 50 seconds. In situations where a direct link failure means this switch directly felt that a failure. The failure occurred in interface to connected link, and one interface was blocking. This is what we call a direct link failure. So to make it faster, if again we lost this interface and switch 1 stopped sending us the BPDUs, we have to immediately start considering this interface as a root port immediately. And to do this, we can enable uplink fast. Here I have enabled spanning tree uplink fast. What happens? Your blocking port will immediately go to forwarding. As soon as you lost the main root port, the waiting timer of 20 seconds, oh, it's not gonna wait. Immediately, hey, this is my new root port. The debug says, hey, I think something happened. But when you do uplink fast, this is something that you have to do it on the access switches, access-led switches only. Immediately, a couple of things are gonna happen. Obviously, as a result, it will whenever a failure occurred, a direct failure occurred, the blocking interface will be put into the root port immediately forwarding. So no 20 seconds, no 15 seconds, again no 15 seconds. So immediately, I'm saying. That's how fast it is. So it will also increase the priority from 32 to 49. It's saying I'm an access-led, I'm an official access-led switch now. Please don't even consider me into any kind of elections. So that's bridge priority is going to be increased. That's one. Link cost also going to be changed. Link cost means, look at this, guys. On switch 3, switch 6, this was the pathway to the root bridge. Now switch 3 had uplink fast enable. Okay, this root bridge, the local bridge priority increased to 49,000. The cost of local interface was 4. The local interface was increased by 3,000. So that nobody considers me as a preferred pathway. Because direct link failure only occurs when the interface is into blocking state. That's why switch 6 says what? If I go from here, the total cost would be 3,008. No, I will consider the interface that has this 4 plus 4 plus 4, 12. So switch 6 went and said 0/1 is my root port with a cost of 12. Because the other option is 3,008, which is not a good option. The only problem with uplink fast here is this is pretty fast, but still that 15-second timer is also there now. After switch 3, finds a new root port, the older entries in switch 1 are as it is. Because if you talk about switch 1, this PC10, look at this. This is gone. Now this port either like put into blocking or whatever it is, but this is not available. Switch 1 still saying this PC10 lives at gigabit 0/1. The traffic is going to backhaul. But to expire these entries, it will at least take 15 seconds because of the topology change notification mechanism. Topology change notification mechanism, it will at least take 15 seconds, so that switch 1 now considers this entry as stale entry and it will remove, and it will perform what? Flooding, so that it will learn a new MAC address from here and say, okay, this new guy lives at 0/0. This is a stale entry. To avoid even those 15 seconds, switch 3 does what? Switch 3 sends dummy multicast frames. And they don't use BPDUs for this case. They have a special type of frames they use here. The switch floods multicast frames using local MACs as the source to instantly update neighbor's CAM address. So they are going to send here the source MAC address, so that switch 2 is going to quickly update the CAM table. So they don't even have to wait 15 seconds. Anything else is a stale entry and is going to be removed from the table immediately. These guys are going to remove this entry from the table, older entry, and if they will inject this saying the PC10 lives at gigabit 0/0, this here. So uplink fast does what, guys? It skips from 52 to 0 seconds. But when you have uplink fast enable on this interface, only then the remaining 50 seconds is also removed. This is not a default behavior. This is done only for the uplink fast. So complete timer is also removed, including that aging timer of 15 seconds is also removed. Everyone with me? Because this is too much, guys. It's like too much theory. If it's too much for the day one, please do let me know. Vijay, you there? Cool.
Yeah, I'm here only. Yeah.
You are understanding everything, right? So
Yes,
far.
yes.
Okay, awesome. So you should understand convergence. Even if you didn't understand something, now you have to tell me what part you didn't understand, and we will try to take it into practical separately. So there is something called convergence. You understood like how the general new topology occurs and converges. Then there is something called reconvergence. Okay, then we talked about direct link failures. In this case, here on switch 3, this interface was blocking. Total time was taking 15 plus 15 seconds for MAC address table update. We skipped that using uplink fast plus the dummy multicast that automatically happens when you enable uplink fast. Now let's talk about indirect link failure. The topology is the same. This guy is into blocking. And I'm not sending any BPDUs, guys. I will never, because this is blocking. Even the BPDUs are stopped from sending here. So what happened here is that failure happened on this interface. But switch 3's gigabit 0/2 is not sending any. Earlier, what was happening? Earlier case, we were into blocking, we lost our interface, and switch 2, when sending the BPDU, now we know we have alternate path. If we didn't receive this BPDU, we wouldn't know. So we are not sending any BPDUs from switch 3, nothing, because this interface into blocking. Switch 2 lost its root port. Do we have any alternate port? I'm not receiving any BPDUs. Because of that, switch 2 will say, hey, I'm the king, I'm the root bridge now. Because I don't see any root bridge. So switch 2 will immediately start sending, because now this is a designated port, right? And only from the designated port we send out what? We send out the BPDUs. It starts sending out BPDU where it's claiming to become the root bridge. This is the switch B. Look at this switch number 2. It's saying, hey, I am the root bridge. It's not the message, sorry, so cost. Look at this cost. Cost is 0. This is look at this root ID. The root ID or something is happening with stone. Doesn't matter. So the root ID and the bridge ID is the same. Someone is claiming to become the root bridge. Now this is heard by the switch 3 on this interface. On this interface. Switch 2 saying, this is a debug output saying, or first of all, let's look at here. Switch 3 says, hey, somebody is claiming to become the root bridge. I'm hearing the root bridge. I heard of someone claiming to become the root with this like a 000B00. That's the switch 2. On 0/2 on interface that is into blocking state. But I also have to wait until my max edge timer expires. I will wait. And then it changes gigabit 0/2 because now it now knows, switch 3 knows, hey, you messed up. You're not a root bridge because I have a root bridge. I have better root bridge than you. Because it is at the same time is receiving a better superior BPDUs. It knows I'm not going to lose my root port, but you cannot be the root bridge. Somebody's having bad dream. It will remove the root blocking state, and at the same time it will start sending. It will keep this interface into designated port, and it will start sending the BPDU of its own version of BPDU. But this was indirect failure from the perspective of switch 3. But still, it waited until max edge timer expires. So after the reconvergence, switch 2 says gigabit 0/2 is my root port now. But still, again, in the indirect failures, we want to make sure we don't want to go through all these things. At least timer should be faster. What basically we want? We want switch 3 to immediately put this interface into forwarding if it receives somebody else claiming to become the root bridge. But it is possible that it may be true. We really have a better bridge. We really have a superior bridge ID now. What is this? What then? Well, it finds out if its own bridge actually alive or not. The root is available or not. It does that. So let's look at the output first. So this is switch 2. Gigabit 0/0 to blocking. I think I turn on this interface later down the line. So here I have enabled the backbone fast, by the way, on switch 3. Okay, I have enabled the backbone fast on switch 3. As a result, immediately when this guy sends the BPDU claiming that I have lost my I've lost my root bridge, my king, and I am the king now, it immediately skips the max edge timer. But it still have to go through the listening and learning. Uplink fast, everything skips. In backbone fast, when you enable this backbone fast on switch 3, it will skip only max edge timer, but still have to go through the listening and learning. As you can see, it is happening here. But at the same time, switch 3 does one thing. When switch 2 have advertises itself, when switch 2 have advertised itself as a root, switch 3 want to make sure, it wants to make sure that if the switch 1 or it's considered king is alive or not. So switch 3 is going to send a special type of packet or special type of frame called a root link query. Root link query. and it does it on our, especially on our its root port. And switch 1, which is the root, is going to say, hey, you know what, I'm here. Please don't do anything stupid. So it sends a root link reply. We are not even talking about RSTP or MST at the moment. This is general span tree, your common span tree, your PVST. So switch 3.
One, just, sorry for interrupting.
Yes,
This
sir. Please.
inferior, in the third point, you have mentioned one inferior BPD. So it is receiving from switch 2, correct?
Inferior is receiving from switch 2. Yes. When it receives
Okay.
that, and then it does these things to verify if my root bridge is alive or not. It doesn't matter whether those 2-second BPDUs we are receiving or not. This is a mechanism that is by default happens. Because you may say, hey, it can just verify from those BPDUs now, right? Why sending separate packet? It can prove this. So that even that 2-second we don't waste. We quickly send the root link query towards the root bridge. Hey, are you there? Are you alive? It's switch 1 is going to reply. It receives the root link reply from the root bridge. And then only it is going to skip the max edge timer and say, hey, I think you have a mistake on something. My root bridge is still alive. I will be the designated port, and switch 2 will do the next steps from there. Are you guys with me now?
Yeah.
Awesome. So this was your PVST, per VLAN spanning tree. Underlying mechanism is basically the first spanning tree. It's just the management is a little bit different. It manages separate instances for each VLAN. So what you're going to do, you're going to watch the video. Definitely I'll send you this PPT as a notes. And here you will be learning about general SPD behavior, convergence, reconvergence, uplink fast. Why do we use that? And backbone fast. Basically, direct and indirect failures. To the very detail, don't skip anything. Now, we will simply compare and what have been enhanced in the rapid spanning tree is what we're going to look at. Your older spanning tree was 802.1D, and it has only one topology tree, and it is very slow. You saw that we had to add so many things and so many updates just to make it faster. A rapid spanning tree came. Okay, rapid spanning tree came. The first was CSTP, common spanning tree. Now we have a rapid spanning tree, 802.1W. It simply reduces the number of steps, and it removes that dependency on the root bridge. It says, hey, I don't have to listen to you every time. I can make decisions by myself. So what happens is you had the disable step. Look at this. You'll understand from here. In normal spanning tree, you have it disabled. Disable is basically interface going down. In rapid spanning tree, is discarding. Blocking is discarding. Listening is also discarding. So you have learning here. You have learning, and forwarding is forwarding. So in here, you have two types of port you were going to see. It's the same, the point-to-point and shared link. Point-to-point is basically, it's saying, in this link, I have a switch or a PC connected, and it's working on a full duplex mode. Shared link is indicating that I have a hub, maybe a hub kind of thing connected in there, right? But in most modern designs, LAN designs that you're going to see, that you will have a P2P link only. But if you want, and the switch have not detected that hub, you also have an option to change the link, spanning tree link type, point-to-point or shared. It depends on what ports have negotiated, if it's a half duplex or full duplex. It was designed in the older days when we had actually hubs in the network majority of the time. Now, if you look at the RSTP BPDUs, we had two BPDUs in the older. Your configuration BPDU was there, And just for the reconvergence, there was a topology change notification BPD was there, right? In RSTP, look at this, BPDU type is always going to be the rapid on multiple span tree. The cool thing is MSTP is just a way of managing things, but for the convergence underlying, everything is running by RSTP. So we don't have to learn MSTP in separately, all those in details. It's actually in short. Here, instead, what we did, we only have a one single BPDU. Good thing. But rather, we have everything is same, like root ID is there, root path cost is there, local bridge ID is there, port ID is there, max, hello timer, forward delay, all those things are the same. We have increased the number of flags here. Here we had older span tree, we had only 2 bits, 2 flags. Here we have lots of different flags. That facilitates our intention. Awesome. We have proposal bit, port role bits, what is the learning bit, forwarding agreement, the topology change acknowledgement bit is also, excuse me, it's not there. Topology change bit is there. So that the second BPDU that we had in earlier case is acting as a flag in there. Is acting as a flag in here. So how topology change works in RSTP? The cool thing is uplink fast and backbone fast is already inbuilt into the RSTP. So if it's a direct link failure, immediately interface will come up. If it's a backbone fast, if it's indirect link failure, somebody is claiming to become the root bridge. Look at this. Here, this is our block port. Link have failed here. This guy says, hey, my root port failed. I am receiving no other hellos, no other BPDUs. I am the root bridge. So it starts sending the BPDU claiming to become the root bridge. The guy that have a block port says, hey, I'm suddenly receiving the inferior, worst hellos from my designated port, from my port that is supposed to be the blocked. I'm immediately going to put the interface into forwarding. And I will start sending the BPDU that I have a better BPDU, and the switch says, hey, I'm receiving hellos with superior root bridge ID. I'm no longer root, and this is my root port now. This behavior is very similar to the backbone fast. It will immediately accept. How does topology change happens here? Because we understood the topology change. But here, anytime any switch, any interface receive the topology change, the same reasons topology change have received, it's going to start a timer, something called while timer. It is 2 times the hello timer. Which is by default 2 seconds. BPDU's hello timer is 2 seconds. If a topology change is detected on a local switch, it's going to run this timer, which is 4 seconds by default. And all the non-edge ports, non-edge designated and root port, basically, all the port that is actually having a switch connected, non-edge ports, it's going to clear all the MAC address table on those ports. And then it's going to send its own BPDU on all the interfaces. It's not waiting to send it towards the root bridge and so that my root bridge is going to convey the message to everyone. It's not waiting there. It is going to send to everyone with a topology change bit set. This bit. This bit. And when everyone sees that, okay, topology change happened, everyone is going to flush out the MAC addresses, learn on that interface. So when neighbor switch receives this BPDU with this topology change bit set, it is going to clear all its MAC addresses on all interface except the one where it received the BPDU with the topology change on. It's just to make sure that we relearn everything. We don't know what is the stale entry now. We're not simply going to flush out everything. And that switch, which received the BPDU, is going to start a topology change again, and it's going to send it to others. It's also going to do that until the timer expires, the while timer expires, which is double time, 2 times the hello timer per second. In normal spanning tree, what was happening? The topology change was conveyed by the specialized BPDU until root bridge tells everyone that, sorry, excuse me, the root bridge tells everyone, hey, something happened, topology change happened, please do that. This topology change with the help of flag is done by every switch here. So everyone is acting like a king. If here I have seen that topology change occurred, I will send that BPDO to upstream switches with topology change. Directly I'm sending. What was happening here, directly this switch is sending. It's sending here, and this guy, except the interface that is received, everywhere, it's going to flush out the MAC address here, MAC address learned on this interface, accept this interface, and is going to send out the BPDU with a topology change flag set to 1. Everyone does that. It's quickly propagated to the whole network.
Okay. In this, like in earlier scenario, topology to change notification was sent to the root, and the root will propagate to a complete topology. Okay. But in RSTP, like the non-root port will send the topology change flag, and the it will be sent via from their links on. It will not like wait for the. It will become. It will go to the root, and root will propagate there. Correct?
Yes, they are not going to, because they are not waiting. It's immediately conveying my message to other switches. Other switches are sending to every other interfaces, root port, designated ports. Only on non-designated ports, they are not going to send. Everything else, they are everywhere else, they will send it.
One confusion here.
Yeah.
Just like you said, like that the below switch, like the non-root switch, has sent the topology change flag set one, okay, to the other switches, and the switches like in the third from below, like it will like it having the 3 links, that it will not flush the MAC address in the below link, but for other 2 links it will flush the MAC.
Yeah,
This
that was
thing,
based on the documentation.
yeah, so in that part I just getting confused. Like it will not like it will like I mean to say like it will not waste time on the like calculating the MAC address or all those things.
No
But
15-second, no nothing. Immediately
okay.
flood. Immediately flush all the MAC address on for this switch, it will flush all the MAC address on these interfaces.
Then again, then it will like again add my MAC addresses later on.
No, I will not add. I will perform flooding, unknown unicast flooding. Generally, how does switch learn the MAC addresses? They flood everywhere, and whoever replies, they will learn the MAC address. The MAC address learning function will happen again, but this is
Okay.
better than having to send my frame somewhere that does not exist. So flooding happens again. We'll relearn everything. Okay.
Then
Vijay,
it can like it can via this mechanism, like we will having like a more delay in my network, like
but
learning MAC address again, like and this
no,
thing by this.
the current switches can learn the MAC address less than one second, milliseconds. But here we have absolute timer. The learning of MAC address depends on how fast the hardware is. But here we have absolute timer, 50 seconds, 15 seconds. Doesn't matter how fast the switch is. You will wait until the timer expires and only then flood that MAC address. Learning is not a big deal. It's like the current TCAM, they can hold on the crores of MAC addresses. Right? They use something called ASICs, application specific integrated circuits, to fasten the switches. So you don't think that flooding, hey, because of the flooding, it's taking the double time. No, it's not going to take the double time. It's super quick. They do
Like
that in the wire speed.
It will flush the MAC address and again re-add. Correct.
Again, re-add, yes, exactly.
Okay, got it.
So, and here the hellos acts like a, kind of a keep alive mechanism. It acts like a keep alive mechanism. If we stop receiving, and it doesn't matter, it has to be the root or the non-root, everywhere, every link. If we do not receive 3 consecutive BPDUs, which is 6 seconds in total by default, the router, excuse me, the switch, the receiving end switch is going to think my sender switch is, or my designated switch is dead. It's no more available. And it's instantly flushes the MAC address for that specific port. This is secondary mechanism to make it faster. We don't confirm. Okay, we waited 6 seconds, that is more than enough to confirm. That's why it's called as a rapid span entry. The last point, how does the actual election and convergence happen here? Initially, think of it like this. They follow, the 4-step mechanism in the common spanning tree that I explained is different than what happens in rapid spanning tree. They follow proposal agreement. Okay, they follow here proposal agreement mechanism. In rapid spanning tree, we'll consider only two switches, the switch 1 and switch 2. Immediately, both of these switches send each other their version of BPDU. Now, switch B immediately realized one thing. My BPDU is not good, and the switch 1 is better. So it basically what it does, it stops sending it. On the other hand, the BPDU sent by the switch 1 have proposal flag set. It's saying, hey, you know what, I'm just proposing to become the root bridge, where I'm better than you. That proposal happens. Switch B at the same time stops sending the configuration BPDUs with the proposal set. So proposal is what happens, and this is its way of telling I would like to propose to become the root bridge. Secondly, the sync happens. Hey, and now switch B knows, hey, so I think I found a root bridge. I'm going to tell everyone I'm going to block these interfaces. It basically blocks these interfaces. And this is very short block. There is no notice there. And it basically blocks these interfaces, other interfaces. That's what a sync process is. In agreement process, it sends its version of BPDU. And inside of it, you will see that it's saying, okay, I see the agreement in there. I'm agreeing, okay, you should become the root bridge. And forwarding means switch A will say, okay, so I have put this interfaces into designated port. This guy can put this into interface as a root port. And this forwarding means everything is fine. The mechanism, the 4-step mechanism is done. After that, this guy can remove this block status on those interfaces. Okay. And it is doing all that using flags only. They communicate using flags only. That's all. This is done between switch A and switch B. Same thing happening with switch B and C. Proposal is sent. They do the syncing for the other interfaces. And they send agreement. And I send my configuration BPDU with the forwarding flag set. And that's how they, here on these interfaces, they become the root ports, and I have to put this interface into designated port. Okay, that was your rapid spanning tree. Now, if we talk about the MST, shall we continue or stop here, guys? Is it going to be too much for day one?
I think we should stop. Day one is too much.
Yeah. Well, that's weekend class is going to be like that, though. But I'll try to be not do too much.